Everyone, and welcome to the Modern Java course. When I first learned Java, I was shocked that it didn't have operator overloading. As I got used to it, I learned to enjoy Java without operator overloading. There are many pitfalls to operator overloading, but I can't deny that it sometimes makes code seems really nice and fluid, especially when dealing with science and math related code. Before I proceed, as usual, the code for this and other videos in the series is available on my GitHub page, so check out this project, store it, and follow me on GitHub. First, we have a simple vector class in which we can use in common vector arithmetics. This sort of arithmetic is very common in physics, 3D, etc. This is common Java code that makes no use of manifold features, or at least so it seems on the surface. We define three floating point variables. We accept them in the constructor, and then we have a plus method. This method accepts another instance of vector and combines them to a result. I can use the vector class by invoking the plus method on it to add both vectors and assign them to a third vector. This is standard practice in Java. It's pretty nice, but it's also not very pretty. In math, we usually just write vec1 plus vec2, and this is understood. With Java, I need to explicitly write plus as a method call, but manifold solves that. Taking two objects that I just created and adding them to one another with a plus sign works seamlessly. It works exactly the same as invoking the plus method directly. And since that method returns a vec object, the result will be assigned to the variable properly. The one problem I have with such code is that I can't control-click on the plus sign and go to the implementing method. I think that's more of a limitation in IntelliJ than in Manifold, though. Let's say we want to write code that uses the plus equals sign to add a scalar, a float primitive to a vector. That would add the floating point number to the three variables in said vector. In Manifold, the plus equals operator is implicit and still works with the plus method, just like the regular plus method. What if I reverse the notation? What happens if I write the primitive value first, like 5 plus the vector object? This will compile to the same code as before and will invoke the plus method on vec with the float argument. The reason for this is that Manifold treats such operators as math operators and will swap their order based on math rules if it can't get a match. Since primitive float has no operator overloading, it will try to reverse the operands. Primitive wrapper objects usually just work out of the box. Java has a wrapper object type for every primitive value. Lowercase float is a built-in primitive. The version with an uppercase letter is an object. We can wrap the primitive in an object as we did here. Since Java 5, this is done for us implicitly. In Java with a feature called boxing, if I assign a primitive value to an object, it will wrap the result in a primitive wrapper. The reverse is called unboxing, and it detects usage of a primitive wrapper and unwraps it. Unboxing works seamlessly here. I'll get back to this subject soon, but first I want to show something else. The manifold signs dependency adds support for big decimal arithmetics. If you aren't familiar with big decimal, it's a Java class for dealing with really big numbers that go beyond the limitations of primitive. This is an important class in the financial sector as well as for math, which must use that class in some cases. In fact, support for operator overloading on that class is probably the biggest reason to use it. Simple arithmetic code just works out of the box with a manifold science dependency. It does exactly what you think and behaves properly. Notice I used the plus sign here, but it isn't limited to that. All operators will do exactly what you expect, and I will get to other operators soon enough. That's fantastic. But what if we want to do something a bit different? Adding a primitive integer to the big decimal won't compile. We don't have a plus method that accepts big decimal in the integer class. But as we learned last time around, we can solve the problem of missing methods with class extensions. If you didn't see that, check my previous video on Manifold that discusses extending Java. We can use extensions to add a method to the integer class. In this case, I'll add a plus method that accepts a big decimal and returns a big decimal as a result. This unfortunately doesn't solve the problem. The code from before still won't compile. The reason for this is that autoboxing doesn't work for this edge case. The compiler treats primitive arithmetic as a special case, so if we add a primitive to anything, the operator overloading won't try to search the wrapper object first and compilation will fail. There's a bad workaround. We can wrap the primitive with an integer object, and this will compile properly, but it goes against the grain of simplifying the arithmetic. We want this to be simpler. Thankfully, we do that using the exact same technique. We extend big decimal with a plus method that accepts a primitive integer. Since operator order can be changed by manifold, this code will get invoked despite the fact that we do 5 plus big decimal and not the other way around. This means we can work with big decimal using fluid simple operators. That's fantastic. Up until now, we only use the plus operator, which also maps to plus equals. The minus and minus equals operator invoke a similar method called minus. The multiply and multiply equals operator invokes a method called times. The division and division equals invokes a method called div. The same is true for the percent operator, which invokes a method called rem. The minus operator applied to a variable invokes the unary minus operator. The increment plus plus operator invokes the inc method regardless of the side it occupies. The increment before or after the variable is irrelevant. The same is true for the decrement minus minus operator. It invokes the dec method. This is about to get crazy. We can override the index operator, the square brackets. Manifold implicitly maps the square bracket operator to the get and set methods respectively. Since the list interface defines these methods, we can treat any Java list as if it was an array by accessing elements based on an index. That's pretty wild. But it's even crazier. This works for map out of the box. That means the square brackets can contain a value that isn't a primitive integer. We can look up a value in a map by using an object within the bracket. This will invoke the get method with that object. Assigning a value to a map is a bit problematic since a map has no set method. It has a pull method, but Manifold already has a ready-made extension that adds the set method for us as part of the Manifold collection dependencies. This can even work for multi-dimensional arrays, but that's getting a bit too deep, so I won't cover that. The final part is relational and equality operators. This is a problematic target for operator overloading. Code that compares two vectors using a greater than operator just won't compile out of the box. But there's a simple solution. We can implement the comparable interface, and its compare_to method will be invoked seamlessly for all these comparison operators. This will apply to greater, equals, greater than, less equals operators, but there are two problems. This is one method that implements four distinct operators. This might not be so simple in some complex edge cases. I might want to return a different result depending on the operator that was invoked. The second problem is bigger. Notice I didn't mention equals and non-equals. The equals and non-equals operators are important in Java. We often do pointer comparison and expect them to work correctly for that use case. But what if I want to override that behavior? The comparable using interface extends comparable and adds some additional methods we can override. It has a method called compare_to_using, which accepts the name of the operator that is used for the current comparison. If we implement the comparable using interface, then Manifold will default to invoking equals when we do a comparison. We can override the equality mode method in comparable using to return identity, which will restore the pointer comparison, or we can point it to the comparable to method. Languages like C++ support overriding even more operators like the new keyword and even the dot itself. These aren't part of Manifold, and I'm not sure they would even be useful given the other features available. Since we won't implement a custom allocator in Java, the new keyword wouldn't make much sense. Finally, I want to talk about a problem with overusing operator overloading and an unexpected side issue. If we look at this code, it seems pretty simple and efficient. But what we really have is something different. We have two calls to the plus methods of the objects here, probably for x and then for the result object returned from that. So this single line will result in two method calls and two object allocations when we only need to allocate one object. Not a big deal if we're doing a bit of side math, but if we're doing high performance math, this can end up very expensive. Normally, when we do vector and matrix computations, we have overloaded versions for adding 3 or more entries. This reduces the amount of allocations and can improve performance drastically. Valhalla might improve the situation, but it's something you still need to mind when using operator overloading. On a personal note, I'm very wary of operator overloading. I still carry the trauma of C++, where it is still a problematic tool. But when we write a lot of math for financial or scientific applications, there is no denying the benefit of using tools like this. In fact, if you're doing any of those, then Manifold has a lot more up its sleeve for you. I will get to some features that are even more amazing in the coming videos. If you have any questions, please use the comments section. Thank you.